Okay, so this is Discrete Optimization, Linear Programming Part 5. So what we're going to see today is some really, really beautiful thing. Okay, so we're going to see duality. Okay, and at a higher level, okay, so you can think of, we are looking at the same thing but from two different angles, and we can see some very, very different things. So most of you have probably seen this picture where you can see this beautiful young lady and this old, ugly woman, right? And so this is duality, right? So this is going to be looking at the same thing, but from different angle. And to motivate you to this lecture, I want to tell you the story of Danzig and von Neumann. So when Danzig invented linear programming, he went to see John von Neumann, so this genius mathematician and computer scientist with this encyclopedic knowledge of everything, right? So he went to see and started explaining the linear programming to von Neumann. And von Neumann, typically a patient, man, was kind of, impatient that day and said, get to the point. And so Danzig said, oh, he wants me to get to the point. And so he started going fast. And then von Neumann stopped him and started deriving all the results and the things that I'm going to show you today, okay? And Danzig was like, what's happening? This guy is just deriving all this on the fly. But von Neumann was also a very kind person, and he said at the end, I just don't want you to think that I'm deriving this on the fly, right? So this is very, very similar to something I'm doing in game theory, okay? And therefore, I'm postulating that these two things are the same, okay? And they are essentially the same, okay? And so that's what that's what I'm going to show you today. I'm going to show you these results on duality theory, which are basically looking at linear programming in two different ways, okay? So what I'm going to show you today is basically two linear programs. The primal, which is essentially what we have been seeing all along, okay, which is minimizing this objective function Cx subject to inequality Ax greater or equal to b with all the variables being non-negative, okay? And then I'm going to talk about another linear program, which we're going to call the dual. And that dual is going to maximize, okay, an objective function, yb. Y are the variables here, okay? So y are going to be called the dual variable. The x are called the primal variables, so, okay, primal, dual, okay? And then we have also a set of linear inequality, okay? Ya is smaller or equal to c. Instead of being greater or equal, it's going to be smaller or equal. Same matrix, okay, different variables, okay? Primal variables, dual variables. And then the y's are also going to be, non-negative, okay? So let me show you an example here so that you can see this on a real example. This is the primal, this is the dual, right? The variable here, the primal variable, x1, x2, x3, okay? You see the coefficient 3, 2, 4, okay? Then you see these two constraints, okay? And then you see the right-hand side, okay? In this particular case, 2 and 5, okay? 2, 5, okay? This is the dual, okay? Instead of minimizing, we are maximizing. We have two variables, the dual variables, okay? And then we have three inequalities here, okay? I'm removing, I'm not showing the non-negativity constraints here, okay? So they are implicit, okay? So primal, dual, you see these things, okay? No, these two guys have a very strong relationship. So I'm going to show you how we obtain the dual, right? So the first thing we do is that we introduce these dual variables, y1 and y2, okay? So in a sense, with every constraint now, we are associating a dual variable, okay? So this is y1 and y2, and of course in the dual is only expressed in terms of y1 and y2. The key point here is to remember these two variables are associated, there is as many dual variables as there are constraints in the primal, okay? Now, how do we obtain the objective function, right? So we transform the min into a max, but the coefficients of these variables, where do they come from? Well, they come from the right-hand side of the inequalities in the primal, okay? So you saw 2 and 5 here, okay? You see 2 and 5 here, okay? And you see now that the objective function is maximizing 2y1 plus 5i2, okay? So in a sense, you take this, you flip it, and you get the objective functions of the dual. Okay, one thing's done, okay? Now, how do we get the right-hand side of the dual? Well, you take the objective function, right? So the objective function of the primal is what? 3, 2, 4 as terms of the coefficient. And now you see 3, 2, and 4 as the right-hand side of the dual, right? So in a sense, the right-hand side of the primal become the objective function of the dual. The objective, the objective coefficients of the primal become the right-hand side of the dual, okay? And now the trick is almost played, right? So the only thing that we need to do is to look at the matrix that you see over there, okay, for the constraints, okay? So we look at the coefficients of of the first column here, so we see y1, y2. We take a column here, the coefficients for x1, okay? They are 2 and 2. And what you get here is essentially the constraints, okay? It's going to be 2y1 plus 2y2, okay, smaller or equal to the value that we had already computed, which is 3, okay? How do we obtain the second constraint? Well, you take the column associated with x2 over there, okay? The coefficients for x2 are what? 1 and minus 1, and therefore these are the coefficients of the dual variable in the second constraint. 1 for y1 and minus 1 for y2, and you get the third constraint. The second constraint. The third constraint is easy, right? There is only one coefficient, and that's the coefficient for the dual variable y2. And so what you see here is that the last constraint is simply y2 is smaller or equal to 4. Okay? So in a sense, it's beautiful, right? The objective function become the right-hand side. The right-hand side of the primal become the objective functions of the dual. And then this matrix, the column here become the row, and the column, of the primal become the row of the dual, okay? And that's how you express this dual, okay? So this, once again, this is without any of the annotation, but you see the primal variable, you see the dual variable. Obviously, if you have two constraints here, you have two dual variables, okay? If you have three variables over there, you have three constraints, okay? So it's going to be this nice matching. It's like you take your head, you flip it, and you get the dual, okay? So that's what you get. So this is even more explicit when you take matrix notation, okay? Remember the last lecture I told you we can view all these things in terms of matrices. This is what you see here as well, okay? So this is the primal. You see the primal variable there, y, x1, x2, x3, okay? So you'll see the dual variable there, y1, y2. These are the coefficients of the objective function for the primal. Where do you find these guys? Well, these guys will be here, right? So they will be the right-hand side of the constraints in the dual, okay? Now you see basically the matrix here, okay? The inequalities is basically the big matrix A, okay? You see the primal variable over there. You see the primal variables here, and what you see here is the right-hand side, okay? So this right-hand side now is obviously going to the objective function here, okay? And you see this matrix here is going to be here, okay? So the only, here the column and the row comes from the fact that here we are multiplying this matrix by these variables, and here we are multiplying you are taking the dual variables and multiplying the matrix. We just switched the side. Okay? So this is, once again, in matrix from primal dual, the objective functions become the right-hand side. Okay, the right-hand side becomes the objective coefficients, and then you have the matrix that you basically switched around. Okay, so that's duality. Now, why is this interesting in any sense? Okay, this is the beautiful property, right? You see the primal, you see the dual, and the basic result that you have is that if the primal has a feasible solution, and therefore an optimal solution, okay, then the dual also have a feasible solution, and it has an optimal solution with the same cost. Okay, so in a sense, these two problems have optimal solution which have the same cost. Okay, now you say you don't know really why this is useful, but I will show you next time, right? So, but this is the basic result. Okay, the basic result is that the optimal value for this one is going to be the optimal value for the other one, and I'm going to just prove it to you. Okay, I'm going to say this x and y. So the first thing that I'm going to show you is that the cost of the primal, okay, is always higher than the cost of the dual. Okay, so think about it. The primal we are minimizing, so we start very, very high, and then we go down, 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 down. Okay, the dual is maximizing. We're going to start at the bottom and go up, 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 up. And what I'm basically showing, the first thing that I'm going to show you is that the primal is going down, the dual is going up, but the dual is always lower than the primal. Okay, so they do this. Okay. They can't cross over, okay? So, and this is the proof, which is very simple. It's very simple algebraic manipulation of these things, okay? So let's x and pi, okay, be solution of, and there is a reason why I'm using pi, you'll see later on, right? So, but x and pi are feasible solution to the primal and the dual respectively, okay? Now I look at the costs. Cx, you see this, okay? So this is the cost of the primal, okay? And now I'm going to use the fact that, these guys have to satisfy some conditions, right? So essentially what I know, look at this thing here. So I know that C has to be greater than y times A, okay? And y is a feasible solution to the dual, right? So here I have pi, which is a solution to the dual, okay? So I know that C has to be greater than what? Than pi times A. And that's what you see there, okay? So you see that Cx has to be greater than pi Ax, okay? So, and I'm just using the fact that this has to be true for a feasible solution to the dual, right? And so the last thing I need to do is use this fact here, which is the feasible solution to the primal. I know that any solution x which is feasible to the primal, is to satisfy Ax is greater than B, okay? Now I have this beautiful Ax over there. I can replace it by B. And what do I get? I get pi B, okay? Now, pi B is the objective functions of what? Of the dual, right? So that's the value of that. That's the objective value of pi, of feasible solution pi. I have Cx over there, okay, which you see here, which is the value of the solution of the primal, and then I have always this relationship that the objective value of the primal is always greater, okay, than the solution of the dual. So they do this, okay. So that's the first result. The primal objective function is always greater than the dual objective function, okay. So Obviously, since the primal is a feasible solution, the dual cannot be unbounded. Once again, we're going down with the primal. The dual cannot just go like this, right? So it has to be bounded, okay? So that's the second fact that I have, okay? And then the third fact, okay, there will be two more facts. The third fact is going to be that at optimality of the primal, I have a feasible solution to the dual. Okay, and this is this pi, of course, right? These simplex multipliers. Okay, why? Because I know that at optimality in the primal, okay, this linear program, I have to satisfy that all these costs, in the basic feasible solution has to be non-negative. Okay, these costs are basically re-expressed in this particular fashion. I've shown you that last time. Okay, so I know that C minus pi A has to be greater than 0. Okay, which basically means that C has to be greater than pi A. Okay. So, which is essentially the condition that we have seen here, right? So this is the condition on the dual. That's a feasible solution to the dual. So what do I know? I know that the simplex multiplier pi have to be a feasible solution to the dual. Hey. So if I solve the primal, I have already a feasible solution to the dual. Okay? So now I can actually show you, with these two facts, I can actually show you that the primal and the dual at optimality have to have the same cost, right? So I take an optimal solution to the primal, x star, okay? And then, obviously, using all the things that we have seen in the previous lectures, I know that the value of that particular optimal solution has to be given in terms of a basis and associating these values to the basic variables, all the non-basic variable being 0. So I know that x star is to be a, b, the matrix for the basis minus 1. I have to invert it times b, which is the right-hand side when I state the system. Okay. Now I told you that the dual has a feasible solution which is obtained by the simplex multiplier. That this is what this is expressing, and the simplex multiplier are simply expressed as cb times ab minus 1. Okay. And therefore, I now can come to this interesting derivation. So the objective value of the dual is this value there that you see, right? So y star b, okay? Now y star, I just gave you the formula there. It's cb ab minus 1. So I have cb ab minus 1 times b. But ab minus 1 b is what? Is the value of the basic variables in the primal. So I get here cb x star. So what I get here is that this feasible solution of the dual has exactly the same cost as the optimal solution to the primal. So I have one feasible solution to the dual, same solution as the primal. I know that there are no solution of the dual that can be better. So what you see here is that the primal is going down, the dual is going up, and then they meet at this optimal point. Okay? So that's basically the result. So you will have the primal, you have the dual. These two programs are closely related, right? So you derive one from the other, and then you know that they have the same objective value at optimality. Okay, so I've shown you the primal and the dual relationship in the general in a restricted cases. So this is the general formula on how to obtain the dual from the primal in full generality. Okay, so in full generality, I'm doing two things. I'm allowing to have equations, not only inequalities, and I'm allowing some variables to be not non-negative. They can take any arbitrary real value. Okay, and once you do that, okay, so you can derive the dual in essentially the same way. There will be some constraints which are equality, some variables which are constrained to be non-negative, and some which are not. How do we get them? Well, look at this thing. Every equality will have a dual variable which is associated with it, and that dual variable here is not going to be constrained. It doesn't have to be non-negative. Okay? If you have an inequality that's these types of constraints, they will obviously have a dual variable, and that dual variable is to be non-negative. That's what I've shown you before, right? And the same thing happens for the primal variables. If a primal variable is non-negative, you know that the constraint we are deriving, like I've shown you before, has to be an inequality, and we know that if the variable is non-constrained, we will get an equality. Okay, so very simple: equalities, no constraints; inequalities, non-negativity constraints. Okay, so that's the general form of the dual. Okay, now there are some very interesting properties for this dual and primal. Okay, so this is basically telling you that the friend of my friend is my friend. Okay, so the dual of the dual is the primal. Okay, so if you take the dual and then reapply the dual of that dual, you get back to the primal. That's a good property to have, otherwise it would be crazy, right? But this is essentially saying if you take the dual of a primal, you get the primal back. Okay? Now, the other things that you have to understand is, what is the relationship if these things are feasible, infeasible, unbounded, and so on. Okay? So we already know that if the primal is feasible, okay, then the dual has to be feasible. If we have a solution, the other guy can get back to that particular solution. Okay? Now, what if the primal is unbounded? Okay? So this is a picture that I've been, telling you. Okay, so when they are both bounded and feasible, okay, so you have the primal going down, you have the dual going up, and they meet. It's like in Pac-Man when they go to the next level. Oh, they meet. Okay, so this is what you have here. Okay, now if the primal is unbounded, what is happening? This guy is going down, 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 down forever, right? And we know that the cost of this guy has to be always greater. The cost of the primal has always to be greater than the cost of the dual. Okay, therefore the dual cannot go up. It can go up. You cannot have a fixed cost for this dual, because otherwise the other one is going through it, and therefore the only possibility for the dual is what? It has to be infeasible, right? So we know that this guy is the primal is unbounded. The dual has to be infeasible. Okay. Now we have the last column that we need to consider, which is, what about if the primal is infeasible? Okay, if the primal is infeasible, can the dual be infeasible, and can the dual be unbounded? Okay, so by analogy to the previous case, you can already reach one of the conclusions. Okay, but this is a very simple example which expresses the possibility. This is the primal. I minimize. Okay, x1. Right? Can it be simpler than that? Okay, and two constraints. Okay, these two constraints are very interesting because you look at the left-hand side here and the other left-hand side. They're just the negation of each other, and they both have to be greater than 1. So this is clearly infeasible, right? So this is the dual, okay? And what do you see in the dual? You see, these variables here are not the variable x1 and x2 are not constrained. So you get equations inside the dual. And therefore, you see some very nice equations where the right-hand side, okay, is the same for these. The left-hand side for these two things are the same, but the constant here is different. Okay, so once again, it's infeasible. So if the primal is infeasible, we know that the dual can be infeasible. Okay, and then there is the other case. It can also be the case that the primal is infeasible, but the dual is unbounded. And the only thing that I did here, I kept essentially the same constraints on the top, so it's still infeasible, but I'm adding more constraints, saying that the variables have to be non-negative. When the variables are non-negative, remember, the impact of that is changing equations into inequalities, and that's what you see there. So now, essentially, you have these two guys here, which have the same left-hand side, okay, but now they are smaller or equal to 1 and 0, so you don't force them to be infeasible anymore. Okay, so these constraints are easy to satisfy, right? So you make just y a little bit bigger than than y2 a little bit bigger than y1, okay? And these constraints are always going to be satisfied. And therefore, what I can do now is take this objective function and drive it up as much as I can, right? I'm basically getting a value for y1, getting an even greater value for y2, and these values can go up, 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 and so it's unbounded, okay? So once the primal is feasible, okay, is infeasible, the dual can be infeasible or the dual can be unbounded. So you know the relationship with this primal and dual now, okay? Now, there is another thing which is very nice, right? So one of the things about the theory of NP completeness is that I told you, okay, these problems are hard. We have to push this exponential, okay? That's what we have been doing all along, okay? But the nice thing about these problems is that we can actually show that if you give me a solution, I can check if it's feasible or not. Okay, very easy. You know, typically low polynomial time. Okay, but proving that something is optimal is kind of tough, right? So I don't have that. Okay. Now in linear programming, can you actually provide me with a certificate of optimality? And the answer is yes. This is nice. In linear programming, I can show you if something is feasible. If I give you a solution, you can check quickly if it's if it's feasible or not. But here you can also convince me that you actually have found an optimal solution. How would you do that? Think about it. How would you actually convince me that you have an optimal solution? Well, this is what you would do, right? So you would say, oh, but you know, we have a primal and you have a dual, you know, okay? So Voigt, Neumann, and Danzig, you know, and some people at Princeton, Kuhn, Tucker, and Gale, if I remember correctly, actually proved this beautiful relation between these guys, this primal and the dual. So now, and so you believe these guys, right? So now you can give me a X star which satisfy, you know, the constraints of the primal. You can give me a Y star which satisfy the constraints of the dual, and you can show me that the cost of these two things are the same. If this is the case, I know then that, you know, X star is an optimal solution to the primal, and of course that Y star is an optimal solution to the dual. So you can actually give me something that I can check very quickly if this is actually an optimal solution. And this is one of the beauty of linear programming. That's the gap between NP completeness and polynomial time. Okay, so we have seen the basic introduction to the dual here, which is beautiful, right? You have this primal and the dual, right? And they have the same objective value at optimality, assuming that there is a feasible solution for both, for one of them, because then there are solutions for both of them. They have this beautiful relationship, okay? And what I'm going to do next time is to show you, you know, what this actually means in practice, and how did we actually get to these things, and why does it make any sense? Okay? Thank you very much.